Bismillahirrahmanirrahim. Assalamu alaikum. Today's lecture is a continuation identification problems. First, we will discuss the identification process, the process which identifies the equations, and we'll do some examples. We'll move through some examples that will show you how to deal with choice of technique, whether you are going to apply ILS or 2SLS. We'll be doing 2SLS later, but today we may take an example which shows exactly identified equations or some over-identified equation. We'll take different models. So today is basically a practice session on how to proceed into looking into the identification status of the equations, and later on choose a technique and try to estimate the parameters of an equation. So let's talk about the process first of all for identification and for solving the models. Remember that we are talking of simultaneous equation models where you have two or more equations. You may have some endogenous variables and some exogenous variables. So the first step in solving such models is to identify which variables are endogenous and which are exogenous. We have some equations and we need the same number of endogenous variables. All the other variables will be called exogenous. Remember that exogenous variables are the variables, the values of which are externally determined from outside the model. And endogenous variables are the variables, the values of which you seek from within the model. You solve the model to get those values. So if you have three equations, you have three endogenous variables and the remaining are exogenous. If you have two equations, as normally you will have two endogenous variables and all the other variables will be exogenous. So when we identify the endogenous and exogenous variables, so if you remember that the structural model, the original model with the simultaneous model has some endogenous variables on the right hand side which prevents us from using OLS or ordinary least square. So what we want to do is to transform the model in such a way that we don't have endogenous variables on the right hand side so that we can seek help from ordinary least square methodology. So we do that by transforming the model into what we call reduced form equations. Let me remind you that in reduced form equations, you have the coefficients called reduced form coefficients. The next step is to use these reduced form coefficients to compute the values of the structural parameters if possible. So look into the possibility. We try to express the structural parameters in terms of those reduced form coefficients. If you remember the previous example, we have alphas and betas as the structural parameters, and we have pi's, pi 1, 0, pi 1, 2, etc. as reduced form coefficients. If we can express the alphas or betas in terms of these pi's, if we can express the structural parameters in terms of the reduced form coefficients, we say that the equation is identified. If we can express them in one way, we say that the equation is exactly identified. If we can express them in several ways, more than one way, 2 or 3 or 4 ways, we say that the equation is over-identified. If we are not able to express these structural parameters in terms of reduced form coefficients, we say that the equation is unidentified or under-identified and we cannot solve it. We cannot find the parameters of an unidentified equation. Let me tell you that if we have a model, it is possible that one equation is unidentified, the second is exactly identified, the third is over-identified, etc. So you may have a mix. So you apply different techniques to solve the model. For example, if you have unidentified equation, you try to find some variables or use some procedure to make the equation identified, to identify the equation. If you have exactly identified equation, the parameters are found by using a technique called indirect least square, which we are going to do in future. So if we have an over-identified equation, we apply techniques like two-stage least square or three-stage least square, instrumental variable techniques, etc. So this is a glance of the procedure or the steps that we follow to solve simultaneous models. So first you identify the exogenous and endogenous variables. Second, you try to write the model in terms of equations that have all exogenous variables on the right hand side, don't contain the endogenous variables on the right hand side. We call them reduced form equations. then we may be able to estimate these reduced form coefficients by applying OLS, because you can apply OLS to equations where you have only exogenous variables on the RHS, the right hand side. After doing that, we try to express these structural parameters in terms of the reduced form coefficients and choose a technique and apply that technique to get the values of the structural parameters with the help of the reduced form coefficients. So this procedure is followed to solve simultaneous models. We have been discussing an example to go through this process to identify the equations, to look into the identification status. And that model contained two equations, one for y1 and one for y2. You had both the endogenous variables on the left-hand side, so it was easy to identify them. But now we'll take an example of the market model where we don't have the endogenous variables all on the left-hand side. We have to identify them on the base of market model theory or market equilibrium theory. So if you consider the demand and supply model, you must remember that quantity demanded is thought to be dependent on price, on income, on tastes, on prices of substitutes, etc. So if we have a supply equation, we think that supply is dependent on price, technology, cost of production, etc. So if we simplify the model, we have only few variables in the equations. Let's simplify the model and go through all the process that we have been speaking of. So look at the model, please. So you are seeing a demand and supply model. You have two equations, one for demand and second for supply. The third is an equilibrium condition. It is not an equation. So you have two equations. You need two endogenous variables. So as you remember, the demand theory and supply theory combined, called market equilibrium theory, try to determine simultaneously the price and quantity, because quantity in equilibrium is quantity demanded as well as quantity supplied. So QD is QS. So Q, the equilibrium quantity, is basically one of the endogenous variables, and P, which is price, which you don't see on the left hand side this time, is also an endogenous variable, and rest of the variables I and T will be considered to be exogenous. So how do we solve this model? Previously, the equations where you had y1 and y2 as dependent variables, you just substituted one in the second and solved it, got the reduced form equation. But this time, you are not going to do that, because you don't have both the endogenous variables on the left-hand side. We do that by using the equilibrium condition, quantity demanded is equal to quantity supplied. So when we do that, as you see in the screen, the model is solved with the help of this condition, QD is equal to QS. We'll use this to get the reduced form equations. As I told you, to solve that, we'll equate the quantity demanded to quantity supplied. Remember that quantity demanded is given as alpha naught plus alpha 1 into price plus alpha 2 into income plus an error term. And quantity supplied is given as beta naught plus beta 1 into price plus beta 2 into technology plus a residual term. If we equate both of them, as you are seeing on the screen, both are equated, and now we have the variables P, I, and T in these two right-hand side and left-hand side expressions. Now what we want to do is to find a reduced form for price. We'll just pick up the terms with price and bring them to the left-hand side and bring everything else to the right-hand side, manipulate it algebraically, and we'll arrive at an expression that you are seeing on the screen, a long one. P is equal to beta naught minus alpha naught divided by alpha 1 minus beta 1 plus some expression into T minus some expression into I plus some expression that contains residuals E2 and E1. So as you know, we just label these expressions in terms of pi. Pi are the reduced form coefficients. So P is given as pi 1 naught plus pi 1 1 into T plus pi 1 2 into I plus V1. V1 is a symbol for the term containing the residuals. So if you see, we have given a different color to the plus sign of pi 1 to I. Why? Because if you look into the above equation, you basically have a negative coefficient of I. So remember that when we label that as reduced form equation or reduced form coefficients, we label them including the sign. So the value of pi 1 2 is equal to alpha 2 over alpha 1 minus beta 1 with a negative sign. So this is why you will always find plus signs in the reduced form equations. This is a good approach. It's a better approach. So the first reduced form equation in terms of price is P is equal to pi 1 naught plus pi 1 1 into T plus pi 1 2 into I plus V1. Now let's look how to get the second one. We'll substitute this P, the reduced form equation for price, into one of the quantity demanded or supplied. You can do that in any equation. So let's substitute in the demand equation. So if you substitute all this in the quantity demanded expression, you arrive at the second reduced form, the reduced form for quantity. For example, you are seeing here that we have substituted the expression, the right hand side expression which was equivalent to price, into the quantity equation, and we have rearranged the terms to bring them together, manipulated them algebraically, and got the second equation where you have as first term alpha naught plus alpha 1 pi 1 naught. We have combined them because both of them don't have a variable in them. So you don't have x1 or x2 or t or I or variables. So this is your intercept basically. You will label it as pi 2 naught. Then you have an expression for the coefficient of t, alpha 1 pi 1 1 into t. So the coefficient of t is alpha 1 pi 1 1. We label alpha 1 pi 1 1 as pi 2 1. So pi 2 1 is equal to alpha 1 pi 1 1. So as you see, we have two terms containing the variable I, the income. One is alpha 1 pi 1 2 into income, and second is alpha 2 into income. We combine them, take income as common, and we have a coefficient of income containing two terms, alpha 1 pi 1 2 plus alpha 2. We label all that as pi 2 2. So the value of pi 2 2 is equivalent to alpha 1 pi 1 2 plus alpha 2. So this is how we get the second equation. Q is equal to pi 2 naught plus pi 2 1 into T plus pi 2 2 into I plus whatever residual is remained, we call it V2. You can use U, V, epsilon for the residual term. So as you have arrived at the second reduced form, and you have already run an example where you had two structural equations, Y1 and Y2, and this time also you have arrived from a market model to a reduced form equation system. So you must note something, that number one, in a reduced form equation, you don't have an endogenous variable on the right hand side. And the second most important is that you have all the exogenous variables in the model, not in the equation, in the model. You have all the exogenous variables of the model as right hand side variables in every reduced form equation. For example, in the reduced form for P and Q both, you have both the variables T and I, which were the exogenous variables. And if you remember the previous example, you had variables x1 and x2, x1 in the first equation of y1 and x2 in the equation of y2. When you got the reduced form, you didn't have y1 and y2 on the right hand side. But also, you had both x1 and x2 on the right hand side of both the equations. So for example, when you had the reduced form of y1, you had the variable x1 as well as x2 as a right hand side variable, although x2 was not a variable in the original equation 1. So we have two properties of the reduced form equation. One, we don't have endogenous variables on the right hand side, and second, we have all the exogenous variables of the model, whether present in an equation or no. If they are in the model, they exist, they are seen, they may be observed on the right hand side of each reduced form equation. So if you know these two properties, you can directly write these reduced form equations even without solving for the model. So now you have a reduced form for price and a reduced form for quantity, and to label them with coefficients pi's or reduced form coefficients, you made some substitutions. For example, you made a substitution alpha 1 pi 1 1 is equal to pi 2 1. So looking into these substitutions, the next step is to try to express alphas and betas, or the structural parameters, whatever you label them, in terms of these reduced form coefficients. If you can't do that, the equation is unidentified. If you can do that in one way, the equation is exactly identified. If you can do that in more than one way, the equation would be over-identified. And we will use different techniques depending on the identification status of each equation. So let's proceed further. So you are seeing the reduced form equations for price and quantity where we made some substitutions which are also given below these equations. For example, you see that pi 2 1 is equal to alpha 1 pi 1 1, and you also see that you have expressions for pi 1 naught, pi 1 1, pi 1 2, pi 2 naught, pi 2 1, and pi 2 2. So let's try to use these substitutions that we made to get the expressions for alphas and betas. If you algebraically manipulate and try to get or try to express betas and alphas in terms of these reduced form coefficients, what you get is given on the screen in front of you. You are seeing, for example, that beta 1 is pi 2 2 over pi 1 2. Beta naught is also equal to pi 2 2 over pi 1 2 times pi 1 naught plus pi 2 0. So you have an expression for beta naught which contains only pi's or reduced form coefficients. Similarly, you have expressions for alphas and betas that contain only reduced form coefficients. So we are able to express both alphas and betas in terms of the reduced form coefficients pi's in a single way. For example, you can express beta 1 as pi 2 2 over pi 1 2 and not in any other way. So as you can do that in a single way, we'll say that as betas, which were the parameters of the supply equation, can be expressed in one single way in terms of reduced form coefficients pi's. So the supply equation is exactly identified. Similarly, you can express all the alphas, which were the structural parameters of the demand equation. You can express them in terms of pi's or reduced form coefficients in one way. So the demand equation also is exactly identified. So in this model, we have solved to arrive at a conclusion that both the demand equation and supply equation are exactly identified. This is the identification status of these equations. From these two examples, you can know that we don't discuss the identification status of the model in particular. We move to individual equations and we discuss the identification status of each equation separately. As I told you, it is possible that we have two different status for two different equations. Until now, we have discussed two examples and we have solved the model to look into the identification status of each equation in these two models. And in both of the examples, all the equations were found to be exactly identified, which is not always the case. So this time we are going to take an example, which I label as example 3, where you have one unidentified equation and one maybe exactly identified equation. So you will come to know that for an equation to be exactly identified, you must have at least one variable in the other equation. This is called an exclusion criteria. The variable must be excluded from the equation in order to make the equation identified. So in this new model, you will see that we have two equations with different structure. We have structural equations, structural model, and when we transform it into reduced form equations and try to express the structural parameters in terms of reduced form coefficients, sometime we succeed and sometime we don't. If we are not able to do that, the equation, not the model, the equation will be unidentified. And if we are able to do that, the equation will be exactly identified. And if we are able to do that in more than one way, the equation would be over-identified. So let's look at the third example for discussion. So as you see, we have two equations. Y1 is alpha naught plus alpha 1, Y2 plus alpha 2 x1 plus an error term E1. Y2 is beta naught plus beta 1, Y1 plus E2, which is an error term 2. Now first let's discuss which variables are exogenous and which are endogenous. The first step, you should remember that as we have two equations, we need two endogenous variables. So how to quickly identify? See which variables are dependent on each other. So roughly Y1 and Y2 are dependent on each other. So we can say that Y1 and Y2 are endogenous. All the other variables are exogenous. So all the other variables are only one, x1. So x1 is exogenous and Y1 and Y2 are the endogenous variables. Now let's try to solve the model as you see on the next slide. So if we substitute the value of Y2 in equation 1 as we did in the previous examples, we get an expression Y1 in terms of x1 and x2. We have only x1, we don't have an x2. So you have one intercept alpha naught plus alpha 1 beta naught over 1 minus alpha 1 beta 1. We call it an intercept. We don't have a variable with that. Then you have a coefficient of x1, alpha 2 over 1 minus alpha 1 beta 1. We will label it as some pi as we do. Plus we have the third part of this equation which contains errors. Whatever contains errors, we bring them together and label them as an error term, which we label here as V1. So you have a reduced form equation, y1 is equal to pi 1 naught plus pi 1 1 x1 plus v1. Let's see how we labeled it. So pi 1 0 shows, as you are seeing on the screen, 1 0 is the subscript, 1, the first part of the subscript, shows the number of equation. So this was the first equation. So we start with a 1. This was the initial parameter, the intercept. We write naught. So 1 naught means first equation's initial parameter. So pi 1 1 means first equation's parameter 1, rather slope coefficient number 1, the slope of x1. Plus v1 is the error term, where we made the labeling or substitution in a way, as you are seeing, pi 1 naught is equal to alpha naught plus alpha 1 beta naught over 1 minus alpha 1 beta 1. Similarly, pi 1 is also equal to some expression in alphas and betas. So we will use this substitution to try to express these structural parameters in terms of the reduced form coefficients. So this was the first reduced form equation. To get the second one, we will substitute the first equation into the second equation. As you look into the next slide, if we substitute the reduced form of y1 in the second equation and solve and manipulate, we get an expression for y2 that doesn't contain y1. We bring all y2 on the left hand side and we have beta naught plus beta 1 pi 1 naught. Both these terms have no variable, so we combine them. Then we have beta 1 pi 1 1 into x1. So x1 has a coefficient beta 1 pi 1 1. We will label this coefficient beta 1 pi 1 1 as pi 2 1. Plus we have two terms containing errors. One is v1 and second is e2. So we will combine them to give them a name v2. So we have a second reduced form equation. y2 is equal to pi 2 naught plus pi 2 1 x1 plus v2, where we made a substitution which is given below. Pi 2 naught is beta naught plus beta 1 pi 1 naught, and pi 2 1 is beta 1 pi 1 1. You can quickly see here that we can easily get the value of pi of beta 1 from the second substitution that we made, that is pi 2 1 substitution or the labeling. So beta 1 is equal to pi 2 1 over pi 1 1. If we have this value of beta 1, we can move to the first substitution of pi 2 naught and get the value of beta naught as pi 2 naught minus pi 2 1 over pi 1 1 into pi 1 naught. This will be an expression for beta naught. So as we are able to express both beta naught and beta 1, which are the structural parameters of the second equation, we are able to express them in terms of pi's reduced form coefficients in one way. So this equation, which contains betas as structural parameters, is the exactly identified equation. But as you will try, I recommend that you try to solve and try to express alphas in terms of reduced form coefficients. Try, but you will fail because you cannot do that. Don't trust me, try yourself. You will not be able to express them in terms of reduced form coefficients. So we'll say that one of the equations is unidentified. The equation that contains alphas is unidentified. As you are seeing two statements on the screen, we can solve for betas, but not for alphas. So only equation 2 is exactly identified, equation 1 is unidentified. And also, you are seeing a second statement which states that the parameters of the unidentified equation have no interpretation because you don't have enough information to obtain them. You cannot estimate them, as you cannot express them in terms of pi's. Even if you have the values of pi's, you would not be able to get the values of alpha indirectly. So this equation is unidentified, where you cannot express alphas in terms of reduced form coefficients. Presently, we have taken few examples, some with all exactly identified equation. The previous one was with one unidentified equation and one exactly identified equation. But as you know, we have another status, over-identification. So when we can express the parameters, the structural parameters in terms of the reduced form coefficient in more than one way, we have over-identified equation. And we cannot use OLS or ILS, the indirect least square. We need to use maybe 2SLS or some other technique. So to clarify, how can we express the structural parameters in more than one way, let's take an example with an over-identified equation. So the model you are seeing is y1 is alpha naught plus alpha 1 y2 plus an error term e1, and y2, a longer equation, is beta naught plus beta 1 y1 plus beta 2 x1 plus beta 3 x2. So you have two variables x1 and x2 in this equation plus an error term. The procedure is the same. You will just substitute the first equation, which is the smaller equation, in the second equation. So the value of y1, which is alpha naught plus alpha 1 y2 plus error 1, is substituted instead of y1 in equation 2. I'll recommend that you do that on paper. When you do that, you will find that y2 can be expressed in terms of x1 and x2. So you have an intercept term containing betas and alphas. You have an expression with beta 2 over 1 minus alpha 1 beta 1, which is a coefficient of x1. And you have beta 3 over 1 minus alpha 1 beta 1 as a coefficient of x2. And you have two terms both containing errors or residuals, that is E1 and E2. Now we label them as usual. So remember that this is the first equation that we get by solution. But I would recommend that since this belongs to y2, the second equation in the original structural model, so when you label the pi's, you use 2 as the first subscript to show that it was from the second equation. So if you look at the screen, you will find the reduced form for this equation. Although this was the first to be solved, but we write the pi coefficients as pi 2 naught, pi 2 1 and pi 2 2 because they belong to the equation y2. This is just to follow a uniform procedure. So when you have y2 in terms of x1 and x2, you have been able to express y2 in terms of the variables x's, the exogenous variables. So you can call this a reduced form equation for y2. Now if you substitute this reduced form equation in the other equation, you will get an expression for y1 which contains only x1 and x2 and doesn't contain any endogenous variable. This is the usual procedure. But when you had this equation for y2, you made some substitutions. That is, you substituted the symbol pi instead of an expression containing alphas and betas. If you look at the screen, you will get these substitutions. For example, pi 2 naught, pi 2 1 and pi 2 2 are equivalent to the expressions that you are seeing on the right hand side of these equations. So you have three substitutions that you made, the labeling that you made for pi's. We will use these to try to express the structural parameters in terms of pi's. Now if we substitute the equation you are seeing on the top, y2 is pi 2 naught plus pi 2 1 x1 plus pi 2 2 x2 plus v2, into the equation for y1, we'll arrive again at an equation which contains only x1 and x2 on the right hand side and doesn't contain y2. So you get a reduced form for y1 which you are seeing on the screen. As y1 is pi 1 naught, we have labeled it as 1 naught because this is the first equation actually, plus pi 1 1 x1 plus pi 1 2 x2 plus e1. Here also we made some substitutions like pi 1 naught is equal to alpha naught plus alpha 1 pi 2 naught, etc. So if you are seeing the substitutions on the screen, you will find that we can express alpha 1 in two ways in terms of pi's. For example, the substitution you made, not the first one, the second and third one, they are pi 1 1 is alpha 1 pi 2 1, pi 1 2 is equal to alpha 1 pi 2 2. You can easily see that first from the second equation, alpha 1 can be written as pi 1 1 over pi 2 1. And alpha 1 also can be written as, from the third equation, pi 1 2 over pi 2 2. So as we are able to express alpha 1 in two ways, in two different expressions in the reduced form coefficients, so we'll say that the equation that contains this alpha, if alpha 1 can be expressed in two ways, this means alpha naught also will have two different expressions when you try to express alpha naught in terms of pi's. So you are able to express alpha naught and alpha 1 in terms of the reduced form coefficients pi's in more than one way. This makes the equation with alphas, the first one, over-identified. And you shouldn't use ILS or OLS. You cannot use ILS. You will use two-stage least square or something else later on. So the first equation with alphas, with the structural parameter alphas, is over-identified equation. And the second equation, as you will come to notice that we haven't shown it here, but if you try to express the parameters betas in terms of reduced form coefficients, you will always get expressions which contain pi's as well as alphas or betas. You will not be able to express betas only in terms of the reduced form coefficients pi's. As you cannot do that, this would be an unidentified or under-identified equation. So this was a model with one over-identified and second unidentified equation. So the parameters of the unidentified equation cannot be estimated until we find some variables and make the equation identified. Remember that the exclusion criterion shows that if you include some other variables, exogenous variables in equation 1, then maybe equation 2 becomes identified. Otherwise, you cannot find the parameters. But the equation 1, which is over-identified, we'll later on learn a technique called two-stage least square or 2SLS to solve for the parameters of this first equation. We will not use OLS because this is a simultaneous model. We will not use ILS because the equation is not exactly identified. We'll use 2SLS, 3SLS or something else. Presently, we have tried to solve models in terms of transforming them into reduced form equations, and then we tried to express the structural parameters in terms of the reduced form coefficients to conclude about the identification status of each equation. But there is an easier way. We can use order condition, or we can later use rank condition. Let's focus on order condition to know the identification status of each equation without even solving the model. This is good because we save time, and we need the solution of substitution that we make for pi's only in case of ILS for exactly identified equations. We wouldn't be needing it for the over-identified equations. So there is no point in spending time in solving models when it is already over-identified. So what we do is shown in order condition. This is a condition that finds the identification status of equations without solving the model, without substituting for pi's, etc. So let's try to understand the two parameters that we would be going to estimate or calculate or just show in order to discuss the identification status of different equations. In fact, we calculate or estimate. We shouldn't use the word calculate because it's very simple. We use the word, we write the parameters P1 and P2. We call it P1 and P2. You can call it anything you like. I call it P1 and P2, parameter 1 and parameter 2. And we'll compare these two parameters and say something about the identification status of the equations individually. Remember that we are going to do this process for individual equations separately. So we have two parameters, P1 and P2. If P1 is less than P2, the equation would be unidentified. If P1 is found to be equal to P2, the equation would be exactly identified. If P1 is greater than P2, the equation will be over-identified. So let's see what this P1 and P2 are. So P1 is basically the number of exogenous variables that are excluded from the equation. For example, if you are looking into the identification status of equation 1, you will see which are the exogenous variables, what is the number of the exogenous variables that are not seen in equation 1. But you can find them elsewhere in the model, in equation 2 or 3 or some other equation. So exogenous variables excluded from the equation is the parameter P1. There is another way to think of it. You can see how many in total exogenous variables you have and subtract the number of exogenous variables in the equation. So the total number of exogenous variables minus the number of exogenous variables in the equation we are discussing gives you the excluded exogenous variables. The number of the variables is called P1. We call it P1 here, the first parameter. The second parameter P2 is defined as number of endogenous variables in the model, not in the equation. In the model, minus 1. For example, if you have two equations, you will have two endogenous variables. And 2 minus 1 is 1. The value of P2 would be 1. And the value of P1 is the number of exogenous variables excluded from the equation. As you are looking at the slide, we have defined P1 and P2. We'll just get their values and compare them. Let's take some examples. Before taking examples, let me repeat the criterion on which we'll base our conclusion. If P1 is less than P2, the equation is unidentified. If P1 is equal to P2, the equation is exactly identified. If P1 is greater than P2, equation is over-identified. Let me remind you that if equation is unidentified, you cannot get the parameters. If the equation is exactly identified, we'll use a technique called indirect least square or ILS. This is a simple technique. You just use the expressions that you find You can express alphas or betas in terms of the reduced form coefficients. You first estimate the reduced form coefficients by OLS, because you can do that, and then use them to get indirect values of alphas and betas. This is called ILS. We'll have some examples later. And if the equation is over-identified, you will use two-stage least square or some other technique. You cannot use OLS or ILS for that. So this helps us in determining what technique we may use in order to get good parameters of the regression equations individually. So as you were told just now that we'll calculate two parameters P1 and P2. Simply, we'll get their values and compare them. And according to the criterion that we discussed, we'll state whether the equation is unidentified, exactly identified, or over-identified. Now example 1. Consider the model with two equations, that is y1 on y2 and x1 and y2 on y1 and x2. You can at once recognize that y1 and y2 are the endogenous variables, x1 and x2 are the exogenous variables. So let's see what are the values of P1 and P2. As I told you, we'll get the values of P1 and P2 for individual equations. So we'll take each equation and look into the values of P1 and P2. So we'll deal with separate equations. We'll not discuss the identification status of the model as a whole. So let's go for equation 1 only presently. So value of P1 is number of exogenous variables excluded from the equation. That is the number of exogenous variables that you find in the model but you don't find in the equation. So as you are looking at the model, you will quickly notice that x2 is the only variable that is excluded from the equation 1. x2 is an exogenous variable and you don't find it in equation 1. So the parameter P1 has a value 1. Now the parameter P2, which is number of the endogenous variables in the model, not in the equation, in the model, minus 1. So you have two endogenous variables, y1 and y2, and 2 minus 1 gives you 1. So the value of parameter P1 was 1 and the value of parameter P2 was also 1. So according to our criterion, P1 is equal to P2, then the equation is exactly identified and we'll apply indirect least square. As you know, you must have noticed, this example is the same one as we had solved the first model that we solved in the process of discussing identification status was this one, and the solution gave us the conclusion that both equations are exactly identified as we were able to express the values of alphas and betas in terms of pi's in one way. So this order condition has verified and is easy that we can understand what is the identification status of models without even solving them. So now let's look at the equation 2. The parameter P1, as you notice, only x1 is excluded. What is P1? It is the number of exogenous variables excluded from the equation that you find in the model but you don't find in the equation. Such variable is only x1 if you speak with reference to equation 2. x1 is contained in equation 1. It doesn't appear in equation 2. So the number parameter P1 is 1. Again, the number parameter 2 is 1 also, because you have two endogenous variables. You subtract 1 and you get the value 1. Again, P1 is equal to P2 and we can say equation 2 is also exactly identified. Remember that we had a long process of substitution. If you would have done it through paper and pencil, you would have yourself solved. You would have taken roughly 15-20 minutes at least to understand what is the identification status. But here we just spent 2 minutes and we knew the identification status of both equations individually by applying order condition. So it is very easy to know the identification status. Let's move to another example. You have the market model in this example that we discussed previously, where quantity demanded is function of price and income, quantity supplied is function of price and technology, and we have an equilibrium condition, quantity demanded is equal to quantity supplied. So again, we have a demand equation and we have a supply equation. We'll discuss the identification status with the help of order condition for each individual equation separately. So let's talk of the demand equation. As you remember from previous discussion, quantity and price are the two endogenous variables. I and T are the exogenous variables. So focus at equation 1 on the screen. You have P and I as the variables. You don't include T. So look at the exogenous variables that you don't find in the demand equation, but you get them in the model. So if you are looking into the model and focusing, you will quickly notice that T is in equation 2 is excluded from equation 1. we call it an excluded variable. And I is a variable that is technically excluded from equation 2 or supply equation. In cases of both these equations, parameters P1 and P2 are equal to 1. So we can say that the demand equation as well as the supply equation are exactly identified. So you can easily conclude that. For example, P1, what was P1? The number of exogenous variables that are excluded from the equation. Or we had an alternative. P1 was defined as the total number of exogenous variables in the model minus number of exogenous variables in the equation. Let's look at this alternative. So you have two exogenous variables in total, I and T. And you have only one exogenous variable in the equation. So 2 minus 1 is 1. So the value of P1 is 1 in case of the demand equation. And the value of P2 is 2 minus 1, which is the number of endogenous variables minus 1. So you quickly must have noticed that in one single model, whichever equation you are discussing, the value of P2 will not change because you have the same number of endogenous variables, and the number of endogenous variables minus 1 gives you a number which remains the same for each equation. The change occurs in the parameter P1, and you have to be equation specific or discuss with respect to a specific equation. So remember, whatever example you do, if you are confined to one single model, whatever equation you are discussing, the parameter P2 will remain the same and the value of parameter P1 will be changed. So compare P1 and P2, remember the criterion, and state the identification status of the model. So in case of this demand and supply model, both the demand and supply are exactly identified. You must have again noticed that this is the same example we had discussed and solved and manipulated algebraically to get the identification status, and we took a lot of time for that. So naturally you must have noticed that we are going to move to the other examples that we have already discussed, but this time we are using order condition to quickly get the identification status of the equations. So let's move to example 3. Here you have y1 and y2, and if you remember, y2, the equation for y2 was exactly identified and the equation 1 was unidentified. Let's see whether this is the case or no by applying order condition. The model you are seeing on the screen has two equations. So first of all, we can quickly conclude that the parameter P2 has a value 1. So as you have two endogenous variables, 2 minus 1 is the criterion for P2. So P2 is 1 in case of both equations. What changes is the value of P1. That is number of exogenous variables excluded from the equation. So now focus on equation 1 on the screen. y1 in terms of y2 and x1. Do you find any exogenous variable that you don't find in this equation? The answer is no. There is no exogenous variable that is excluded from this equation 1, because in the second equation you don't have any exogenous variable. So in this case, the value of P1 is 0. You have no exogenous variable excluded from equation 1. So as P2 was 1 and P1 is less than P2, and the criterion is that if P1 is less than P2, the equation is unidentified. So the first equation is unidentified. Now focus on equation 2. y2 is beta naught plus beta 1 y1 plus e2. P2 will remain the same, 1, that is 2 minus 1. And now P1 is the number of variables excluded from this equation. The number of exogenous variables that you don't find in this equation, but you find them somewhere in the model. So there is only one such variable, that is x1. So P1 is 1. So as P1 and P2 are equal here, the second equation is exactly identified. So for an exactly identified equation, we apply the technique of indirect least square, which we are going to discuss in future. So ILS is a technique that you apply to solve for the parameters of equation 2, that is beta naught and beta 1. But unfortunately, you cannot apply any technique to get the values of alpha naught, alpha 1 and alpha 2, because you are not able to express them in terms of pi's, because order condition also specifies that equation 1 is unidentified. So until and unless you find some variables to be included in equation 2 to make equation 1 identified, you are not able to get the parameters alpha naught, alpha 1 and alpha 2. So remember, we had another example. Let's move to that one. If you remember, the model you are seeing on the screen has two equations, and if you remember, the first equation was over-identified and the second was unidentified. Let's verify this situation. In case of both the equations, P2 is equal to 1. I would recommend that you just, before I tell you think of the values of P1 for both equations. And when I tell you, see if you are thinking correctly. Now focus on equation 1. How many variables you see in the model that you don't see in this equation? There are two variables, x1 and x2, that you see on the right hand side of equation 2, and you don't see them or observe them in equation 1. So this means the value of P1 is 2 for equation 1, and the value for P2 is 1. That is 2 minus 1, number of endogenous variables minus 1. So as P1 is 2 and P2 is 1, P1 is greater than P2, and the order condition states that if P1 is greater than P2, so equation should be over-identified, and it is over-identified. So we normally apply 2SLS or some other technique. When you move to equation 2, look at equation 2 again, try to think. Do you find any exogenous variable in the model that is not contained in this equation 2? The answer is no. There is no variable, there is no exogenous variable that is excluded from equation 2. So the value of P1 for equation 2 is 0, and the value for P2 is again 1, because this remains unchanged within this model. So as P1 is less than P2, equation 2 is unidentified, and as I told you, no method can be used for that. So presently you have been discussing models with two equations. What if you have three equations? The model you are seeing has three equations. Y1, Y2 and Y3 are seen on the left hand side, and you have several variables, y's and x's, on the right hand side. Observe that Y1 depends on Y2 and Y3, Y2 depends on Y1 and Y3, and Y3 depends on Y1 and Y2. This model was not solved earlier, so we are relying on the order condition to discuss the identification status of each equation separately. So let me tell you about equation 1 only, and the rest I leave to you. We have two parameters, P1 and P2. P1 is the number of exogenous variables excluded from equation 1. Let me repeat it. The number of exogenous variables excluded from equation 1. This means the number of exogenous variables that you find in the model, but you don't find in the equation. So if you look at the model, you have three variables which are exogenous, x1, x2 and x3. But x1 is present in model 1, in the equation 1. There are only two variables that are not included in equation 1, x2 and x3. So the number is 2. You have two variables. So P1 is 2. This time P2 is 2 instead of 1, because you have three endogenous variables, y1, y2 and y3. And P2 is defined as number of endogenous variables minus 1, so you have 3 minus 1 is 2. P1 was also 2 in the case of equation 1, and P2 is also 2. As P1 is equal to P2, the equation should be exactly identified, and you should apply ILS. So if you quickly, by using a paper and pencil, you try to get the values of P1 and P2 for the rest of the two equations, you will quickly notice that all three equations in this model are exactly identified. So what order condition tells us that we just compute or get to values of two parameters and compare them, and without solving the model, we quickly can decide about the identification status of each equation separately, and we save time for solving the model. So in case the equation is unidentified, you have no point in solving for that, because you will never be able to get the values of the parameters until you change the model, until you include some variables, for example. If the equation is found to be exactly identified, then yes, you will need to solve for the values of structural parameters in terms of the reduced form coefficients, because you will have to indirectly get these structural parameters from the reduced form coefficients by using the reduced form coefficients. We will do that. And the third case, over-identified equations. If the order conditions tells you that some equation is over-identified, let me tell you beforehand that when you discuss two-stage, least square, etc., you will notice that we don't need to get the expressions or values, because you remember we have two or more expressions of the structural parameters in terms of reduced form coefficients. We can express the structural parameters in terms of the reduced form coefficients in more than one way. So if you try to apply ILS, you will get two or more values for the same parameter, and this is meaningless. Which value is correct? Both are wrong, in fact. So you wouldn't be getting values, some unique values for the parameters. You cannot apply ILS. And when you apply two-stage least square, you don't need these expressions. These expressions are in fact useless because you have two or more different expressions for the same parameter. They are not giving you a meaningful value. The order condition is a very helpful method to guess about the identification status of equations. I would recommend that you visit the sites on the internet, Google, and find different models and try to apply the order condition just for practice so that you are perfect in guessing about the identification status of each equation. The goal is that you look at the model and at a glance you at once tell me or tell your teacher or tell somebody else that the equation is exactly identified, over-identified, or unidentified. So, in fact, there are two ways to know the identification status of equations in a simultaneous model. The first way is to solve for the model, find the reduced form equations, use the reduced form coefficients and the expressions to try to express the structural parameters in terms of the reduced form coefficients, and your success will tell you whether the equation is identified or no. And the other way, if you only want to know the identification status and you don't need the expressions, you will just apply order condition, compute or look at two parameters P1 and P2, which we labeled P1 and P2, and compare them, use the criterion in order condition and just state the identification status and act accordingly. By act accordingly, I mean if the equation is unidentified, try to find more variables to make it identified, to change the model a bit. If equation is exactly identified, apply indirect least square. If the equation is over-identified, apply two-stage least square. We'll come to know what are ILS and 2SLS basically. So in today's lecture, you learnt about useful ways to discuss the identification status of equations in a simultaneous model. First, you practiced by solving, and then you looked into a useful technique, which is order condition. Thank you very much.